All right, guys, so this next video, we finally got past all those definitions and terminology and stuff like that. We're ready to start talking conceptually about what is sound. Now, you may have heard the question before, if a tree falls in the forest and nobody's around to hear it, does it make a sound? We're going to answer that question today. All right, so here we go. The first thing I want to do is show you a couple of demos. So come with me, let's watch. All right, guys, so a couple of demos to help us figure out what exactly sound is, and then we're going to talk about how we actually hear sound. All right, so the first one is simple. I got a ruler here on the table, and when I push it down, you can hear a sound. But what happens if I move it? All right, hopefully you heard that. Okay, we'll do it again. All right, so we're getting some different sounds there, right? When I pluck the ruler. Okay, let's look at another one. Another one you're probably familiar with. Okay, so we got a rubber band here, and I'm just going to pluck it. All right, so plucking a rubber band. Another one is tuning forks. Okay, so I've got a tuning fork. What I'm going to do here is I'm going to hit it, and hopefully you can hear that sound. All right, some different pitches. And I like to show this one, even though it's a little bit different, but I want to show you what happens if I take it and put it in the water. See what happened? Ah, there you go. That time we saw it, right? Splatters water everywhere. All right, now I want you to think about, what do those different demos have in common? They all created sound. Why? What was happening there? Okay, well, hopefully you recognize that the thing in common was that they all had vibration, right? Vibration is necessary for sound, right? In the one case, the ruler was wiggling up and down. In one case, I plucked the rubber band and it was vibrating back and forth. In the other, I hit the tuning fork, and the tuning fork, even though we can't necessarily see it, it's vibrating really, really fast. In fact, you notice because when I put it in the water, it splattered water everywhere. Well, that's because it was vibrating back and forth so fast. Now, for example, this one right here is 1,000 hertz. Now, you may remember from our class discussion that hertz is how many cycles per second. What that means is that when I hit this one, it vibrates back and forth 1,000 times per second. That's how fast. That's why when we hit it, we can't really see it vibrating, right? Even if I give it right up to you, you're not going to really see it vibrating because it's vibrating so fast. But when I put it in the water, we see the water splash everywhere because of the vibration back and forth. And it does slow down. It mutes it pretty fast. Okay, but that's going to be really important as we continue our discussion here. All right, vibration. Sound requires vibration. So I hope that started to kind of make sense. What I'm going to show you now is another video. This is a video of a situation where we have something kind of like a tuning fork. It's made out of plastic, so the vibration isn't quite as fast. It doesn't have as high a frequency as maybe the tuning forks would. But what you'll see is that the ends of the forks vibrating very fast. And it won't look super fast, but then it'll actually go through in slow-mo. All right, so let's go ahead and have a look at that. Okay, so there's the plastic. He pinches it and releases it, so it's vibrating back and forth. And it almost looks like you can count it as it vibrates back and forth, but this is the reality, is it's going back and forth so fast, right? This is slow-mo, so we're only half a second in. It's already gone back and forth 18 or 19 times, right? It just keeps going, vibrating, vibrating, vibrating. This is what's happening to the tuning fork, but remember the tuning fork had a frequency of 1,000 hertz, so it goes back and forth 1,000 times in a second. So this is what we're talking about, a full cycle going back and forth, back and forth, back and forth. The frequency is that many times. This one got up to about 30, what was it, 38? 38 times in a second. That would be the frequency, right? So that kind of helps you conceptualize a little bit what's happening. Now, a frequency of 38, that is on the very low end of human hearing. Humans can usually hear everything between about 30 hertz, that's their frequency, right? 30 hertz, up to about 30,000 hertz. Now, the older you get, the less able you are to hear those frequencies, especially the high ones. Okay, anything below that you probably can't hear, but you can probably feel, because you can feel the vibrations. If you have really good bass speakers, sometimes the sound isn't so much about the sound as it is about the feel of the vibration that you get there. All right, so let's go ahead, we'll move along to the next little piece here. Remember, this is a sound wave. This is how sound works. Okay, we've been talking about that idea of the vibrations, right? Well, I pointed out in the previous video this rod vibrating back and forth. This is like your tuning fork. This is like your rubber band that's vibrating. This is like the ruler that's vibrating. This is like your vocal cords in your throat, which you cause to vibrate as the air passes over them, right? You get those vocal cords to vibrate. It's all about the vibration, because when it vibrates, the vibrating objects hits the molecules in the air. And the molecules in the air then hit other molecules in the air, which hit other ones and hit other ones and hit other ones. And the vibration then causes the sound wave to travel through the air. Now, it happens obviously much faster than this, but that's what we're looking at here, is that it's vibrating. That object vibrating vibrates the molecules in the sound. They bump into others, until finally that vibration gets to your ear. All right, now we're going to talk about how we then interpret that as sound. So I got my picture of the ear here, right? The first thing is that the sound is focused on the outer ear, but then it focuses it in. It goes through the tunnel and all the way to the eardrum here. The eardrum starts to vibrate, right? Why does it vibrate? Because the molecules of the air are hitting it. That's literally what's happening, is that the motion of the molecules is bumping into the eardrum, causing it to vibrate. Now, when it vibrates, there's some fluid inside here that also vibrates. When it vibrates, there's some little hairs that are on the inside of your ear that then start to vibrate. As those vibrate, they cause an electromagnetic pulse, which then gets sent up the nerves into your brain. And then your brain takes those electrical impulses and turns it into, it interprets it as sound. But really all it is vibrations that your brain is interpreting as sound. Now, it's pretty weird to think about that all these sounds are really just vibrations and that we're just interpreting it as sound, but it's also really cool that we can use those vibrations to do this weird thing with their vocal cord to create speech, which then we can interpret as sound in speaking, right? This is some cool stuff, all about the vibrations. Now, this is very similar to what happens when you use a microphone and a speaker, right? When you use a microphone, you, again, create vibrations, which causes the air to vibrate, vibrates all the way to the microphone. When it gets to the microphone, there's something inside the microphone that vibrates and turns those vibrations into an electrical impulse, just like the little hairs turn that into an electrical impulse that goes down to your brain. But in the microphone, that electrical impulse then goes through the wire to the speaker, and when it gets to the speaker does the opposite, kind of like what the brain does. The speaker interprets it, but the speaker turns it back into vibrations. Now, it can actually take that impulse and it can make it bigger or smaller or whatever else. It can change the pitch, the sound, the volume, whatever. We're going to talk about all those things in our next module, but it basically takes that electrical impulse and turns it back into vibrations, and you can feel that. You can feel the speakers vibrate. Sometimes if it's a really low frequency, you can actually see the speaker vibrate inside of your box there. But that's all it is. It vibrates, which then causes the air to vibrate again, and it gets to your ears and causes that whole process to go over again, right? And so that's all that's happening when you use a microphone and a speaker. It's basically the same thing that happens inside of your ear. The eardrum is like your microphone, and then it gets translated to electrical impulses into your brain, which then turns into the speaker, where it turns into what you actually think that you're hearing, when it's really just vibrations. Pretty cool stuff, right? Now, I do want to close with what we started with. Tree walking in the forest, falls, does it make a sound? Well, it all depends on the definition of sound that you're using. I got these 3 definitions from the Merriam-Webster dictionary, which is a pretty commonly used dictionary. One of them just says a particular auditory impression. That one we're not going to worry about. The sensation perceived by the sense of hearing. Now, if we use this definition, it's the sensation perceived by hearing. So therefore, if there's nothing hearing, if there's no sensation being received by the sense of hearing, then no, there's not a sound. By this definition, it says that there must be a receiver. Otherwise, it's just vibrations in the air. It's not sound. So according to this definition, we'd have to say, no, the tree doesn't make a sound. Does it make vibrations and those vibrations vibrate the air? Absolutely. But if there's nothing to receive the sound, then there is no sound, according to this definition. But the third definition, yep, just going to cloudy things up again. The third definition says mechanical radiant energy that is transmitted by longitudinal pressure waves and is the objective cause of hearing. Whoa, there's a lot of big words there, but this ties into what we've been saying for the last day, right? We're talking about mechanical energy, right? Mechanical waves that's being transmitted by longitudinal waves, right? They call it pressure waves because when it's compression, there's high pressure, and when it's rarefaction, there's less pressure. So that's why it's saying longitudinal pressure waves. This is just longitudinal waves. So mechanical energy being transmitted by longitudinal waves and is the objective cause of hearing. So it's the thing that causes hearing. And so this is just talking about the wave, the energy that's being transported, the vibrations. And so by this definition, yes, it does make a sound because it does create those vibrations, whether something is there to receive it or not. So you make your choice. What definition do you want to use? Based off of how you're defining sound will be the answer to the question. Does the tree make a sound? Well, it definitely makes those vibrations. It definitely makes that sound wave, which you could define as sound. But no, there is no receiver, so therefore it does not make a sound in that sense of the word. All right. That's it. So now you understand what sound is. It's just a bunch of vibrations that are being transmitted through the vibrations of the air molecules from one place to another as that energy gets transported as a wave. We're going to talk a lot more about sound over the next couple of days, so hang with me, and I'll see you next time.